Hello again, this is Mr. Baker and I've got another physics video for you guys. Today we're talking about 1D inelastic collisions and we're going to do a couple of examples and solve them with conservation of momentum. So in inelastic collisions, momentum is conserved as always. So final momentum is equal to initial momentum. However, kinetic energy is not conserved, which means that the change in kinetic energy will not be equal to zero. That's going to really irritate me because I drew that the wrong direction, and if I have to look at it for the rest of the video, it's going to drive me nuts. There we go. So there is some change in kinetic energy. So to solve these, we have to use conservation of momentum, and that's all we can use to solve them. Let's jump right into a couple examples. In 57, you have a man standing on a lake, frozen lake of ice, and he wants to get over to the shore because who would want to be standing in the middle of the lake, right? So we know that the shore is 5 meters away. We know that in order to get over the shore, he's going to try to throw his shoe in the opposite direction to see if he can get himself over there. So we know that the mass of the person is 65 kilograms. We know that the mass of the shoe is 0.15 kilograms. And we want to know how long it'll take him to travel those 5 meters. So to find that out, we're first going to have to find out how fast he can move. We need to know something about his velocity. This is an explosion problem, basically. You have two things that are together, and they're exploding and they're separating, which really is just a collision in reverse if you think about it. So let's solve the initial momentum of our system. When we're looking for momentum, we have to, momentum of a system, which you've learned, we look at each individual part and we add it together. So we have the momentum of the person, which is mass of person, velocity person, plus momentum of the shoe, which is mass of shoe, velocity shoe. Now, like I said, they're stuck together, so the velocity of the person, and that's the initial velocity, is equal to the initial velocity of the shoe. That initial is really important so you don't get confused, because this is not going to be true in the second part of the problem with final momentum. This is only true initially. So because that's true, I'm just going to call this new variable v initial, and I'm going to distribute it out, and I can take mass of the person and mass of the shoe and distribute out my velocity, make this a little bit easier to solve. Also, we know that he's just standing still on the lake. He can't move because there's no friction, so he can just slide his feet, but he won't go anywhere. His velocity is 0, which makes his initial momentum 0. Now we know, because of conservation of momentum, that initial momentum is equal to final momentum. So that means that final momentum is also equal to 0. So let's look at final momentum now. Just like last time, we look at each of the parts. So we've got the shoe. Now he throws it to the left at 2 meters per second. So I'm going to put that in our diagram. And that's going to cause him, he hopes, to move to the right with some velocity so that he can get over to the shore. So the momentum of the person is the mass of the person times the velocity of the person, and the momentum of the shoe is the mass of the shoe times the velocity of the shoe. We can put in some information we know. We know that's 65. We're looking for the velocity of the person. We know the mass of the shoe is 0.15, and we know the velocity of the shoe, this is important, is negative because we've set positive to be in our right direction. Really should be a straight line if we're being, perfect here. We've set positive to be straight to the right, so that has to be a negative. From there, we remember right up here, final momentum is 0. So you can solve that equation for velocity of the person. I'm not going to do it for you because I don't want to waste your time. Now, in this situation, momentum is conserved, right? But we have some kinetic energy now because initially when we started out there was no velocity. V initial was 0, so there was no kinetic energy because kinetic energy is 1/2 mv squared, right? But now we do have some velocities. We have a velocity of a person and we have this velocity of the shoe. And kinetic energy is not a vector. We don't really care about direction, so the kinetic energy is going to be some number not equal to 0. So where did that energy come from? And I want you guys to think about that, and we will talk about it in class. It's actually pretty interesting. That energy had to have come from somewhere, and if you think about it, you might be able to figure out where it did come from. I'm going to move on to another problem, but this I will show again at the end of the video if you want to see it one last time. So in the next problem, which is problem 62, you have one car. It's my excellently drawn car. I'm going to call it mass 1. It's moving to the right at 25 meters per second. And you have car 2 over here, and I'm going to call it mass 2. And depending on the part of the problem, A, B, or C, its velocity we don't really know about. It's going to depend. It's just kind of chilling over here. So in part A, we're asked to find out the final velocity if these two things collide, if M2, if the second car was initially at rest. So that means that its velocity would be 0 in this part of the problem. Okay, so same as last time, momentum is conserved. Let's find our initial momentum. I have two components in this system, m1v1 the first car plus m2v2 the second car. I already know that v2 equals 0, so that term goes away. Oh, and we're given the masses. M1 is 1,200 kilograms. M2 is 1,500 kilograms. So I can plug that in for now. And just like last time, we've set right to be our positive right direction. Okay. So that's our initial momentum. We know because of conservation of momentum that's equal to our final momentum. Our final momentum, once again, these two things come together and they collide and they stick together. So this is like future M1 stuck to M2. So mass 1, velocity 1 plus mass 2, velocity 2. Remember this is final now because final momentum, final mass, final velocity. Mass never really changes in these problems, so we don't have to worry about that. But that's not to say it couldn't if you had a rocket burning fuel or something like that. So it's important to know that all these variables are final variables. All these variables are initial variables. Okay, just like last time, now they're stuck together, which means their velocities should be the same. So I'm just going to call that V final now. And because I know that, I can distribute out V final just like I did last time. And the left-hand side of our equation we know is Pi because momentum is conserved. So I can put that together. You guys can solve for V final. It's a big question mark, not a 0. It's non-zero, I promise you that. I'm not going to waste your time with it though. And it's very similar to the first problem, so hopefully that is adequately explained. However, if you have questions, please bring them to class and ask them. We are very happy to answer questions on the videos. In part B, we want to know what happens if M2 is initially moving to the right at 20 meters per second. That's easy enough. That means that the initial velocity for 2 equals 20. That means that this term will not be 0, so you have to account for it. you'll have it something like this. And everything else from there is exactly the same. That'll show up down there, and it just changes the numbers, but the setup is exactly the same. And that's the same for part C too. What happens if M2 is initially moving to the left at 20 meters per second? Okay, we can do that. Now, this time, it's negative 20 because we've set positive to be that way. I feel like I occasionally beat a dead horse with something like that, but it is important to really get. So this would be negative, right? Not plus. And that will also be reflected, and the setup is exactly the same, the numbers are just different. So you know the setup, and from that you can solve any of these problems. In this problem, unlike the explosion problem, kinetic energy is lost. And I want you to think about where could it have gone, and we will discuss that in class. So that's it for the video. I'm going to leave this page up. You can pause it right now if you need to look at it for a little bit longer. So go ahead and pause, and now I'm going to bring up the first problem if you need to see it a little bit more. And that's all. I know that was a little bit longer than my last video. I'm sorry to disappoint you. I know some of you are probably in some emotional trauma because of that, but don't worry, I'll have another short one for you eventually. That is all for now, and have a good day, guys. Bye-bye.